Okay, welcome back to the Tutor Wizard. Please subscribe right here. You'll get notifications for, if you hit the bell and all that, you'll get notifications for this series and other series I have on my channel. What we're going to do is we're going to continue with the Math 120 final review with 2 or 3 problems at a time. We'll see how this one goes. And then I'll release a whole series of these, and then you can watch them 2 or 3 at a time and try to digest for the final exam. What we're going to do is solve this linear system S, which is 2 by 2, and we're going to solve it not using row reduction or Kramer's rule or anything else. This time what they ask specifically for is for us to view it as an AX equals B, find the inverse, and solve for X. Let's do that. First of all, I see that the coefficient matrix of this system is 1, 1, 1, minus 1. We have to find the inverse of this. Quickly, let's compute the determinant. The determinant of A is AD minus BC, which in this case is AD 1 minus 1 minus 1 times 1, which is negative 2, which is not 0. So A minus 1 does exist, and this technique applies to this system. If it's not square or this doesn't exist, we can't use this technique, and there's not a unique solution to this system. Because we did get non-zero, there will be a unique solution, and we can find it by inverting A and solving for X. Let's do that. A inverse is 1 over the determinant of A times the adjoint of A, or the cofactor matrix transposed. What is that? Well, that's, in our case, for the 2 by 2 case, this is, we already computed the determinant, so that's 1 over negative 2 times, the clever trick is you interchange negative 1, 1, and then you add negatives to the off diagonals. And so this is A inverse. I'm going to leave the scalar multiplication on the outside because we have to multiply by the vector B, which is, I forgot to list, but 3, 2. So in this case, that's what they're saying. We have AX equals B. We're going to solve for A now. Okay, now that we have the inverse, what that says is we're viewing this as A 2 by 2 X, which is our unknown vector, which is 2 by 1, equals B, which is 2 by 1. What they want us to do is solve for X explicitly. We now have the inverse, and we know it exists, so we can multiply both sides on the left by the inverse. What does that give me? That gives me A inverse AX, I associate on this side, equals A inverse B on this side. A times A inverse is identity. Identity times X equals A inverse B. And identity times a matrix, or a vector in this case, doesn't do anything, which is, leaves us with, our solution is X equals A inverse B. You don't have to derive this every time on your exam, but this is essentially the algebra that shows us how to solve any size n by n system uniquely for the unique solution. If the determinant is non-zero, there's a unique solution, and we can solve it by doing this. This says X, which is our unknowns, X1, X2, is equal to A inverse B, which is negative 1/2 times negative 1, negative 1, negative 1, 1, times B, which is 3, 2. I erased it, but it was 3, 2. Again, this is matrix multiplication, 2 by 2, 2 by 1. Inside indices match. The outside will be 2 by 1 again. This equals negative 1/2. I leave the constant on the outside, and now I multiply on the inside. This gives me negative 3 plus negative 2 is negative 5. And negative 3 plus 2 is negative 1. And that gives me the unique solution. X is, I can now distribute that in, 5 over 2, 1/2 is the unique solution. Good. Number 4. Okay, number 4, what we're going to do is, we're given 2 vectors u and v in 3 dimensions. They've got 3 coordinates, so I'm in R3. What they want from us is to compute u dot v, the norm of v, the projection of u onto v as a vector, the vector projection, and u cross v. So these are types of things that you have to use in a bunch of different problems. You should probably be aware of how to do them separately or together in a problem. Right now, this one's just focusing on doing the pieces of a bunch of tools that you should be using in other ones, specifically lines and plane problems. 1. 1 and 2 are actually prepping for 3. I need projection of u onto v is u dot v over norm of v squared times the vector v. So these are in preparation. U dot v is equal to 3, negative 1, 2 dot product with 1, 0, negative 2, which is equal to 3 times 1 plus negative 1 times 0 plus 2 times negative 2, which is equal to, this is 0, so I have 3 minus 4, which is negative 1. 2, the norm of v is equal to the square root of the sum of the square of the coordinates, 1 squared plus 0 squared plus negative 2 squared, which is the square root of 5. Therefore, the norm of v squared is going to be the square root of 5 squared, which is just 5. Why did I do that? Because I can do the first 3 all in one, and then we'll erase and do the cross product to remind us of that. But for now, for the projection 3, the projection of u onto v as a vector is u dot v over norm of v squared. That's all a number, the scalar multiple, times v. What does that give us? Now I've computed those things. That gives me u dot v was negative 1 over norm of v squared, 5 times v, which was 1, 0, negative 2. Scalar multiplying that in, that gives me negative 1/5, 0, 2/5 is the vector projection of u onto v. For the last one, let's erase this and then recap what this is and remind ourselves how to compute u cross v in a meaningful, efficient manner. Remember, for u cross v, we view this as a 3x3 determinant where we cofactor expand along row 1 and we put I, j, k as a11, a12, a13. What does that mean? We write a 3x3 determinant, I, j, k, and then we are going to cofactor expand along row 1 where I put a11, a12, a13 as I, j, k, and then I put u and v as the rows of the other 2 rows. 3, negative 1, 2, 1, 0, negative 2. If you put them in backwards, you'll get v cross u, which is negative u cross v, because now we can see in determinant rules, anytime I interchange 2 rows or columns, I would get a negative on the outside. So you'll still get an orthogonal vector, but technically it has to be u in row 2 and v in row 3 to get u cross v. Computing this, again, cofactor expansion along row 1 means that I'm going to use a11 c11 plus a12 c12 plus a13 c13, but specifically for cross product, that becomes equals I times the 2x2 determinant by blocking off row 1 and column 1. So negative 1, 2, 0, negative 2 minus j times 3, 2, 1, negative 2 plus k times blocking off this and this, I get 3, negative 1, 1, 0, which is equal to, what do I get? This now gives me I times 2 minus j times negative 6 minus 2 is negative 8 plus k times, that's a vector, k times 0 minus minus 1 is 1, which gives me the vector 2, 8, 1. Is that right? I don't know. Let's check. On the gamma specifically, they give me a problem where at the end I can compute to tell whether I'm correct or not if I remember what I'm doing. This vector has to be orthogonal to both u and v. And what is that Pavlovian nerve that it hits? If they're orthogonal, that means their dot product has to be 0. Let's check that. What do I get? I'm going to get u dot product with u cross v is equal to 3, negative 1, 2 dot product with 2, 8, 1, which is 6 minus 8 plus 2, which is 0. Check. If you check it with V, I'll leave it to you, but check with V also and you will get zeros because these are orthogonal to both. So this is the correct vector that we were supposed to get. Next question. Okay, for number 5, what we're going to do is we're going to look at and determine whether each of these transformations from Rn to Rm, whatever dimensions they are whether they're linear or not. For those that are linear, they want us to find the standard matrix for that transformation. What do we have to check first of all? A, I guess. Does 0 go to 0? That's the easiest one. We have a result that says if t is linear, then t of 0 Rn maps to 0 Rm. 0 maps to 0 if it's linear. We can use the contrapositive. If t of 0 n does not equal 0m, this says t is not linear. That's what we want to use. That's the first condition I would always check. And indeed, in this case, that's the easiest one to check because it's not going to map to 0, so we're done, not linear. But this is what I'm using, the contrapositive of the statement that says, if you're linear, then 0 maps to 0. So the contrapositive of that is, if it's not mapping 0 to 0, it's not a linear transformation. So t of 0 is equal to t of 0, 0, which is equal to 0, 1, 0, which does not equal 0, 0, 0, which is the 0 in R3. Remember, this is the 0 in R2, is what they're talking about. It's different when you're in different dimensions or different vector spaces, which are abstract. What does that say? 0 didn't map to 0, so t is not linear. You can check, or if you look at the solutions on Blackboard, these are also, for my classes, these specifically, I show the details of the other 2 axioms where it doesn't split sums and it doesn't spit out scalar multiples. So it fails all 3 axioms. Okay, for this one, A, we're going to see if 0 maps to 0, and it does. T of 0 R3 is equal to t of 0, 0, 0, which is going to go to what? 0 minus 2 times 0, 3 times 0 plus 5 times 0, which is 0, 0, which is 0 in R2. So 0 maps to 0, check, good. It doesn't mean I can't use the converse. Just because 0 maps to 0, I can't say it's linear. But if it doesn't map 0 to 0, it's not linear. So now if you get 0 to 0, you check the other 2 axioms. Make sure all the rest of them are true. B, t of k times x. Remember, what does that look like? K times a vector. This is t of scalar multiplication in 3 dimensions is going to be kx1, kx2, kx3. Where does t send this now? It sends it to x1, so kx1 minus 2 times kx2. 3 in the next coordinate, it's 3 times x3, kx3, plus 5 times kx2. Now I look, is there k in each of these terms? So all I'm doing is showing that there's a k in both coordinates. Yes, there is. Factor it out. I get kx1 minus 2x2 in the first coordinate and k3x3 plus 5x2. Can I pull the coordinate out? Yes, this is scalar multiplication in reverse. This is k times x1 minus 2x2, 3x3 plus 5x2, which is equal to what? K times t of x. So it spit out scalars. Check. This is t of x. It tells us. Now what do we have to do? We have to look at a sum. Let's write that down. X plus y is going to look like x1 plus y1, x2 plus y2, x3 plus y3 in R3. That's coordinate-wise addition. What do I do with that? Now I apply t to that and see if it splits it. T of x plus y is t of x1 plus y1, x2 plus y2, x3 plus y3. What does that do? The definition of what it was, I just erased it, but look back if you need to. That's equal to a 2-dimensional coordinate, which is let me leave myself some room first. I'll write it out. It was the first coordinate, x1 plus y1 minus 2 times the second coordinate, x2 plus y2. And then the second coordinate was 3 times the third coordinate, x3 plus y3, plus 5 times the second coordinate, x2 plus y2. Now what I'm going to have to do is see addition in reverse. First I'm going to group the x's together and group the y's together using the arithmetic rules of the real numbers, and then we'll split it as 2 vectors. This is equal to grouping the x's and the y's together, x1 minus 2x2 plus y1 minus 2y2. In the bottom I have 3x3 plus 5x2, 3x3 plus 5x2 plus 3x or y3 plus 5y2. Now I see that that is the sum of the 2 vectors. This one plus this one. He's missing a bracket. So that equals x1 minus 2x2, 3x3 plus 5x2 plus y1 minus 2y2, 3y3 plus 5y2, which is what? This is t of x, and this is t of y. This is t of x plus t of y. Therefore, t is linear. It sent 0 to 0. It spit out scalars and it splits sums. So this is a linear transformation. Therefore, what do we have to do? We have to find its standard matrix now. This is our transformation. If this is our transformation, t from R3 to R2, where it does this to every vector in 3 space, we want to find the standard matrix of this. You can do it 2 ways. I'll do it both ways for the review sake. You can use it whichever one you want. First of all, what I view it is, this is how what they did originally. We want to view this as multiplication of a matrix on the left. So if we do that, we want to say that t of x is the same thing as a times x. First of all, we look, x is 2 by 1, and that says we have to have what as the outcome? Or maybe I should write it like this. x1, x2, x3 has to equal, sorry, that's a 3 by 1, has to equal the outcome y, which is going to be 2 by 1. That's better. And our y vector is 2 by 1. And what is that vector? The vector they gave us, that is going to be x1 minus 2x2, 3x3 plus 5x2. None of these markers work. This is a 3 by 1 vector that I'm talking about here. And this tells us now the size of the matrix we have to get. We have to get a 2 by 1, and the inside indices have to match, so this has to match, and then we have to have 2 by 1 to get the outcome. Now I know what the size of the matrix is. What I'm saying is moving t like this to these points is the same thing as multiplying on the left by a matrix of this vector. How are we going to get this? Well, in the first row, it's going to be this row dot product this to get the first entry. And what do I need? I need a 1x1, negative 2x2s, and 0x3s. And then 1 times x1 minus 2 times x2 plus 0x3 will give me this exactly. And then in the second row, what do I need? It's switched around, but I need 0 x1s, I need 5 x2s, and I need 3 x3s. And that will give me, this technically it will give me 5x2 plus 3x3. But that's still what we've done to get that. That says this is the standard matrix. The standard matrix of that transformation now is A, which is the standard matrix of t, is equal to 1, negative 2, 0, 0, 5, 3. If you didn't like that, we can also use the theorem that tells us we can look at what the standard matrix is. The columns will be the images of the standard canonical basis vectors in R3 under T. What am I saying? Basically this. In R3, I have E1 is 1, 0, 0. E2 is 0, 1, 0. And E3 is 0, 0, 1. To find the standard matrix from these, we look at what t does to each one. T of E1 is t of 1, 0, 0, which is equal to what? It sends us to 1 times x1 minus 2 times this minus 2 times 0, 3 times 0 plus 5 times 0, which gives me 1, 0. What's t of E2? T of E2 is t of 0, 1, 0, which is equal to 0 times 0 minus 2 times 1. And in the second row, I'm going to get 3 times 0 plus 5 times 1. And this gives me negative 2, 5. And t of E3 is equal to t of 0, 0, 1, which sends me to 0 minus 2 times 0. And then in the second row, I get 3 times 1 plus 5 times 0, which gives me 0, 3. What do those give me? That says the standard matrix of T is now T of E1, they say, column T of E2, column T of E3. And that gives me the 2 by 3 matrix, 1, 0, negative 2, 5, 0, 3. This is how you compute. Please subscribe right here. You'll get notifications for this series and a bunch of other series I have on my channel. I'll see you next time. We're going to do a bunch more final review problems.